Alright, so in this video we're going to show how to arrive at the variance of residuals using matrices. So recall that our model, our linear model, is y, which is a vector of y's, right? So an n by 1 vector, equals x, which is our design matrix, times beta plus epsilon, which is a vector of model error terms. Right? And we have made the assumption that the variance of epsilon equals sigma squared times I, where I is our index matrix, right? And that assumption yields the result that the variance of y is also sigma squared times I, because x is non-random, right? And we have that y hat, our predicted y values, equals x times b. Okay, and previously we showed the least squares estimator b, what this guy is, b equals x prime x inverse times x transpose y. Okay, so I can plug in this b, right? So y hat, this guy is going to equal x times all this jazz over here. So this is times x transpose x inverse times x transpose y. Okay, and this front matter here, all right, so I'm building it up to finding the variance of the residual, but first I need to pause here because this guy is very important, and as we continue, we're going to continue looking at this guy, and what we call him is the hat matrix. Okay, so H equals x times x transpose x inverse x transpose. Right, so this guy is called the hat matrix. He's very important, and we will continue using him throughout the rest of our discussion of linear regression. Okay, so let's think about what the dimension of this hat matrix is. So x is n by however many parameters you have. So if you have 2 parameters, then it's n by 2. Right, so the intercept and the slope. Okay, then x prime, or x transpose, is 2 by n, then x is again n by 2, x transpose is 2 by n, and so all of your middle terms, they should all cancel with each other, so this guy cancels. When you take the inverse of a 2 by 2, it's just 2 by 2, and then 2's cancel, and what are you left with? You're left with an n by n. So H is an n by n. Our hat matrix is an n by n. Okay, and H, it's very special. So first thing is that H is symmetric. So H is symmetric. And the second thing that you need to know about H is that H times H equals H, right? And you can show this. It's actually not too hard to show, so let me go ahead and do that. So H times H is x transpose x inverse x transpose. That's the first H. And then the second H is x transpose x inverse x transpose. That's the second H. All right, and we see some nice things happen here. So these guys, they're being multiplied by each other. Notice that this one is exactly the same as this one, except that one's inverted. So when you multiply them by each other, they cancel, right? And that's the result, basically. So what happens now is you're left with H transpose H equals x, okay? Now, those blue guys, they've gone away, and I'm left with x transpose x inverse times x transpose. And voila, look, that's exactly what H is. Okay? Okay, so we're going to use this as we're deriving our variance of the residuals. So now, having this set up, we have y hat equals h times y. Okay, and that's going to make our life a lot easier. All right, so let's go ahead, let's get to it. So we have our residuals equal y minus y hat, right? Which is exactly the same thing as saying y minus hy, because y hat is just hy, right? And basically we can pull out a y. Well, it will come out of the back because this guy's in the back. So we'll end up with I, right, our index matrix, minus h times y. Okay, so now when I want to, let me go ahead and scroll down. When I want to figure out the variance of those residual terms, this is going to be the variance of I minus h times y. Okay, so basically this is a matrix that is non-random, because remember h only involves x's, which are non-random, and then y, which is random, right? So this is going to equal I minus h times the variance of y times I minus h prime, right? So remember, when you basically remember this property of the variance, so variance of a times y, where a is non-random, this is a times the variance of y times a prime, right? And that's basically the property that I just used. So basically here a is I minus h, okay? All right, and I know the variance of y, right? And I scroll up, that was a result of my model assumption was that the variance y is sigma squared times I. So let's go ahead and plug that in. And I'm left with I minus h sigma squared times I minus h prime. Right? And this sigma squared is, of course, it's just a scalar, so I can pull it out to the front. And I can drop that I because, you know, it's just the index matrix there, so it doesn't do anything, so I can go ahead and drop it. And I'm left with sigma squared equals I times I minus h transpose. All right, and I can simplify this. First, let me go ahead and bring this transpose in. Of course, when I bring the transpose in, I transpose is just itself. And H transpose is also just itself because H is symmetric. So basically that transpose, it didn't matter. And now I can multiply, so I times I, right, which is just I, because that's just a bunch of ones. H times I, or actually let me go, next one is I times H. I times H is just H. Now H times I, it's just H. And then h times h, so that'd be positive, h. Okay, so let's see what I have here. I have I minus, this is, I see two h's, so let me write that as minus 2h. All right, and then h times h is just h, so that's plus 1h. So you have minus 2 h's plus 1, and you're going to be left with, there's only one negative h there. All right, so there you have it. This is the variance of the model residuals, right? And of course, sigma is unknown. This is our model error, unknown. So what do? We plug in mean squared error here, right? Which is s squared, which is E transpose E, right? So the sum of squared residuals divided by n minus 2. All right, so you can plug in that s squared to estimate the variance of our model residuals.